Good evening, everyone. Sorry for the slight delay, I was just in the kitchen grabbing a drink. Hope we're all doing fine on what has been a sunny Sunday in the UK, thankfully. I've actually just got a glass of ice water. You know, Claire could have brought me a cup of tea, but no. Thanks, Lucas. Glad you're enjoying it. Yeah, thanks, Peter. Yeah, look. Ice water. Right. So, what have I been doing? I have been doing some jiggery-pokery with how we go about forming the planetary body in a star system. I've gone at this in several different ways over the past month or so, and I think where certain things aren't working is because we're doing it artificially. We're arbitrarily defining planet type based on a dice roll, and that's not really astrophysically correct, as much as we're using boundaries imposed by astrophysics. It's not how star systems form, so the resulting star system isn't particularly organic. It's a little bit predictable. So what I've done is I've taken a slightly different approach to how we go about generating each planetary body. So I'm using the core accretion method. So essentially, every single planet starts off as a rocky core, and then the eventual type of planet depends on what happens after that initial rocky core has formed. Because every planet, even the gas giants, although Saturn's debated, they all have a rocky core somewhere in their midst, because that would have been the initial clump of matter in the protoplanetary disk that obviously grew bigger and formed the planet itself. So that's how we're doing it. So all we're doing is we're simply using a curve, i.e. this, and this is our mass curve of the protoplanetary disk. So obviously the further out of the system you get, the more mass there generally is in order to form planets. So at the top here we've got 10 Earth masses, which is the cutoff really for a terrestrial world, all the way down to 150 trillion kilograms, something like that. Essentially, it's a roundabout Triton. So it's the smallest mass really you can get and hold on to an atmosphere. So that's our mass range, and we apply that as the maximum value. So minimum value is the mass of the moon, and then the maximum value is whatever value that is on the curve, and then that's obviously randomized. And we've still got our 1% chance of something odd, and in this case the only something odd we have is just a dwarf planet. That will be expanded upon in time, so that 1% oddness can be all sorts of different things. Things like a gas giant that's had all of its gas envelope stripped away, so it's just literally the core of a gas giant, like a solid iron lump, which could be quite cool. So that gives us our initial planetary mass. Now, obviously, for a terrestrial planet, that will end up being the actual mass. For a gas giant, that's literally just the core of the gas giant. And I've tried a few different approaches to this, and I think the most logical step is to then define the gas envelope, which really is just telling us whether or not it's going to be a gas giant. So the way I'm going to do this, and this might end up needing to be tweaked depending on what we end up with, but we have a curve for planetary mass. So up here at 10 Earth masses, there's a 0.5 chance of being a gas giant, and that goes down all the way to 0%. But also on top of that, we've also got the chance of a gas giant increasing as volatiles in the system increase. So the further you get away from the star, the more volatiles there are that can accrete into the atmosphere of a gas giant, and that caps at 0.5 in the other direction. So what that means is, if you're far away from the star and the planetary mass is 10 Earth masses, then that's essentially 100% chance there's going to be a gas giant, because you've got this massive terrestrial body in the area of the protoplanetary disk where all the volatiles are hanging out, and a planet of that size is going to capture all of that matter. So that's pretty much a guaranteed gas giant. So these curves work in tandem with one another to kind of balance out just how much matter there is. Which is what I was just doing here. So this value plus this value gives us our chance for a gas giant. So we need a random pool from stream. Then we need our stream. Be random with weight. So combining these curves together, if they add up to 100%, then that's definitely true, and that will definitely be a gas giant. So if it's false, it's rocky. If it's true, it's a gas giant. And this base planet, Enum, really only needs two values at this point, because ice giants and gas giants are essentially the same thing. Yes, ice giants have a higher methane component in their atmosphere, but not by much. It's more the temperature of the gas giant that defines its characteristics, because of the upper cloud layer and what clouds form depending on its equilibrium temperature. So really, ice giant is a term we use for the Sol system, but becomes a little redundant when you have a much wider range of gas giants. Yes, Peter. So when we generate the initial star, we take like 0.015% of the star's mass, and that is essentially the protoplanetary disk. And then we use up chunks of that mass as we're generating planets until there's none left. Yeah, so the Zdarsky scale gas giant classes are decent enough, but not granular enough. Again, they're based on gas giant temperature. So yeah, class 3, 4, and 5 gas giants are still gas giants. The only thing that makes them class 3, 4, 5 is their temperature range that they're placed in. And we're going to do that in a much more granular way, with a lot more classes than just the Zadarsky ones. We have a lot more exoplanets as an example now to go off of. Okay, so we've determined here that whether or not the planet is a gas giant. I was going to forego a simple dice roll to define that and actually use the gas envelope itself, so that the gas envelope of a planet is fully fluid from 0 to 13 Jupiter masses worth of mass in volatiles. But the problem with that is that's a huge scale. So you're literally going from like the atmosphere of Mars, which is like nothing, all the way up to 13 Jupiter masses. And in order to plot that on a graph, even like at like 0.1%, you're already like several orders of magnitude more atmosphere than Earth has. And it just doesn't work very well. So it's better at the moment, until I find a better way of doing that, to decide whether it's a gas giant based on the mass of the initial body and where it's placed in the solar system, and then work out from there how much atmosphere it has, because we can then use gas giant scales of atmospheres if we know it's already a gas giant. Yes, Sentiment, we're working on defining planetary bodies in more detail with a view to adding life. Things like atmospheric composition and whether or not it's breathable for humans. Yeah, I looked at log scales, but again, the issue with it is the massive range of values that we're dealing with. Like 13 Jupiter masses compared to the mass of Mars's atmosphere is such a wide range that tiny increments result in huge values. But obviously you can make that like hockey stick graph really, really steep. But it's going to take some fiddling, I think, before we get to that point. This will do for now. At least to prototype the life generation. So I think what I want to do with this is we'll go ahead and decide the atmosphere from here. Or we go with the just sticking to the base planet type, so at least by this point we know whether we're dealing with a gas giant or not. The elemental composition, I've been researching all the various compositions of the sole terrestrial planets, and also looked at a really interesting paper that went into quite a lot of detail about the magnetic field of a star and how that affects the protoplanetary disk. And I was able to draw an ion saturation curve from that, which is nice and straightforward. essentially the further away from the star you go, the less and less iron is available in the protoplanetary disk. And this scales pretty much perfectly, actually. So you kind of got Mercury around here with 60% odd, Earth and Venus around here, equilibrium about 288, yeah, 33% odd, which is exactly what it is in the real world. And then Mars has an equilibrium temperature of 210, about there, and Mars has about a 20% iron count overall of its planetary makeup. So this curve fits the solar system perfectly, which is nice because that just kind of nailed it first time. So we know really accurately how much iron exists on a planetary body, and then from there we can work out the other chemical components, such as silicon, magnesium, oxygen, etc, etc, etc. So at least we know what's on the surface, and then we do the same job for the atmosphere as well. For example, Earth has quite oxygen-rich rocks, although not as rich as Mars, funnily enough. Mars has a lot more oxygen and a lot less iron in its actual overall planetary makeup. Yeah, when it comes to stars and how we go about doing that, obviously we have a distribution of class, which is well documented in the scientific community. So we are scattering stars by class based on their known distributions. When it comes to things like supernovas, nebulas, like planetary nebulas, that sort of thing, again, we'll probably do the same there. We'll use known distributions, the average number of that class per light year cubed, and we'll scatter them throughout the galactic disk based on that, and also based on the galactic structure as well. Yeah, and then of course you've got the population 1 and population 2 stars as well. There are some population 2 stars in the galactic core, and all the arms are population 1 stars. And obviously in the galactic halo, it's mostly population 2 as well. And they're not metal rich, so the absence of metals and heavy elements in those stars obviously affects the star system itself and what can form. So if the star itself doesn't have any heavy elements and is just hydrogen and helium, then that's all the planets can be as well, because that's what made up the protoplanetary disk. So we will be taking that into account when we get to that point.
Mm-hmm.
So something else I was looking at is I found a really good website, which I don't think I have the link to, or do I? Oh yes, I do, this one. So apologise for blinding everyone. But this site is really good at showing the relationship between mass and radius for planets. And if you kind of skim through all the data, this table here, of which there's a much more detailed version of it, shows you the mass of the world based on its metallicity, which is really, really handy. So, for example, Earth mass 1, 30% iron, which is kind of what Earth is, practically 1 Earth radius. So what I've done is I've taken this table, or more specifically this version of the table, which is a bit of a mess, but there's a lot of data there, I've taken that and I've converted that to a function. Where did I put it? Here. So the importance of deciding how much iron there was on the planet was so that we could do this. So one of the issues I noticed with the planetary data in game, once planets have been generated, is that the density and the radius values are wrong, and therefore the gravity is wrong as well. And that's because we're guessing at what the densities would be for that planet, and then how better to describe that. So we were taking the mass of the planet, and then we were using the core mass fractions. We were working out what fraction of that planet was the core, the crust, and the mantle, and then we were deriving the radius from that, and therefore the density, which wasn't giving us good values. But because Harvard did that study of all exoplanets and put together that graph, we now have a really nice mass versus iron count lookup table, which we can use to give a much more accurate planetary radius. So, let me just find where it was. Yeah, so now that we know what planet type we're dealing with, we can bring that into play. So we need to, determine what our surface iron fraction is. Then we can use that to determine the radius and the volume, and then we can do our layer densities from that instead and work it the other way around. Because we've had this sort of chicken and egg problem all the way along, where we've got the mass, and then we can guess at the densities, and then like mass over density gives you your volume, but it's getting it the right way around. Hey Leo, welcome to the stream. Don't worry, we haven't done much yet. I've just been going through what I've been baking my brain with over the past couple of days. Right, so we need to replace these with our new iron fraction. And again, we're determining the iron fraction from that curve based on the protoplanetary disk and the star's magnetism. So yes, this is giving us our planetary radius. And obviously that's only that only really applies to terrestrial worlds. So for gas giants, we'll have to do the same as we were doing before. Oh yeah, definitely. If I don't leave myself notes like this, then when I look at it in 6 months' time, I'll be like, why did I do that? Now I'm going to try and squeeze in life generation on this stream. The prerequisite to that is working out the atmospheres. And the prerequisite to the atmospheres is working out atmospheric pressure. And we can't work out atmospheric pressure unless we have accurate gravity values. and the gravity was always about 30% wrong. So we need to solve that problem first. Yeah, I don't think I'll quite manage another 5-6 hour stream today. I was up at 7 a.m. So yeah, I've been up for quite a while. I don't usually get up that early, so I'm not used to it. Right, so we don't need to care about icy bodies because we're rolling that into this now. Yeah, thanks, Peter. I'm definitely working on it. I have a glass of water instead of Fanta. That's a good start. Yes, and the Earth analogues will be true Earth analogues, not just randomly deciding if it's an Earth-like based on its temperature. Yes. Yeah, so when we actually get down to putting players on planetary surfaces, all of the data we're generating here will directly apply to that planetary surface. So if the gravity is extreme, then it will affect the player in an extreme way. So one of the confusing things when looking at real-world data is a lot of the data sources don't agree with one another. Depending on where you look, you get different values for things. And one of those things that tends to vary where you look is just how big planetary cores are. So it should be the case that Earth, Venus, and Mars have approximately 50% of their radius taken up by the core. And that's that's more like 70% with Mercury. So we need to take that into account. Yeah, it's hard to trust the science when they all disagree with one another. Yeah, so when it comes to extreme environments, there's definitely going to have to be things like encounter suits and various technological assistance to aid the player, because we want to model our surfaces realistically. So if it's like minus 300 Celsius on the planetary surface, then you can't just walk around in a t-shirt. Right, so borrow these two here, because we're going to have to change the order in which we're doing things now. do that bit in isolation, and then we'll do these bits. Right, so we've got our radius, and then we use our radius to determine the volume, and then we take our initial planetary mass, although to be honest, is it even an initial mass at this point? I suppose it is, because for gas giants we need to add more mass onto that for the gas envelope. Which we're not doing here. Base. Yeah, well, I'm hoping the shuttles will be big enough to also include vehicles. In fact, they're going to have to be. So the shuttles need like a little bay at the back where small vehicles can fit. So there should be plenty of room for, suiting up. I'm trying to do all these steps in unison for all planet types, but I think I may have to deviate slightly from that plan. Just handle gas giant atmospheres before I move on. I'll write something sensible there at some point. Yeah, we could transport vehicles separately, but I'd rather do it all in one go. And we won't need to make the shuttles too big. I'm thinking seating for maybe 6 people, an equipment room, and then the hangar at the back where you can park a vehicle or just fill it with cargo. The vehicles won't be huge. Yeah, we do hope to have a range of ground vehicles, so there has to be some flexibility there. Yeah, that would be bad. Yeah, maybe not quite that extreme. No worries, Leo. Have a good one. So this is our gas envelope. Now that we're doing this separately, we can do so. I believe 0.41 Jupiter masses was the kind of cut-off point where you get like super Earths into water planets and then like mini Neptunes. So I'll use that as our baseline. Again, the further you go from the star, the more volatiles are available in the protoplanetary disk. And also, if you're right up against the star, then the chances of the gas giant having had its atmosphere stripped is quite high as well. So, armed with this, we're using our equilibrium temperature. Float curve, and there's our magic value, and then we want to do random float in range from stream. So we're using that curve as our max value, just to make sure we don't have anything too extreme within the system. Right, and this is a mass value, so we need to take our our initial mass, and then we also want to have the mass fraction. So that plus that. Ooh, actually, I've just thought of a flaw in my cunning plan. This curve is based on Jupiter masses, not Earth masses, so I just need to do a conversion on that. Yes, Logan, it's about 90% blueprints so far. There are some bits of C++ for critical functionality, but the basic stuff is just blueprints. Essentially, anything real-time is C++, anything that's event-driven is blueprints. So Jupiter is 317.8 times more massive than Earth. So we shall times that by 13. That gives us our magic number of that. No, not straighten, flatten. Okay. And then the low ends. So that would be 317.8 times 0.41, which is 130 Earths. Oh, no, wrong way around. Oh, that's right. Oh, comma. Always doing that. Right, so that's a bit of a mental range, but again, this is the issue. When you've got 13 Jupiter masses worth of mass, the range is just huge. And that's the problem with making a logarithm. So that's now outputting a fraction of Earth masses, and we're adding that onto our planetary core. That gives us our initial mass fraction. Then we need to times that by 10 to the power 24. Yeah, that gives us our initial planet mass. Yeah, I'm continually on a daily basis just amazed and kind of frustrated with how huge space is, because it makes life very awkward. Actually, at this point, this is kind of no longer the initial mass, this is actually the actual mass. So we don't need to worry about the initial value. And then if we're not a gas giant, then we can just go ahead and transfer that across to the other variable. No, I didn't want to do that. Tidy that up a bit. Yeah, so if we're a gas giant, then we use our curve to determine how much of a gas envelope we have in kilograms. If we are not a gas giant, then our planetary mass is essentially just the rocky bit. we'll add atmosphere on top of this afterwards. Right, so we have our final masses. We've then got our iron fraction. So the next thing to do then is to take the mass that we have just done. That one. Wow, that is pretty insane. Yeah, so I guess it's our radius, our volume, and our average density. I'm going to have to rename this to mean density, because it's not the true density of each layer, it's the mean density of the whole planet. That's fine, because we can work the gravity out from that. Now that I've renamed that, it's going to error a bunch of times. Oh, it didn't error. Wow. Right, so we should be able to now do the gravity. For that, we want to switch to our final mass. And our radius. Okay. So I'm going to have to work out the layer densities slightly differently. Because we've got our planet radius now, which we didn't have previously at this point. So we can work backwards from the radius to work out the density of the various layers of the planet. But to test it, I'm going to skip that for a minute. This is now atmospheric composition. We've already determined whether or not there is an atmosphere. So we don't need that. Just do that for now. Actually, no, we weren't setting those up, so that's fine. Leave that there temporarily. So we don't need to do this, which is what we were going to do to determine if it has an atmosphere. And we don't need to do that either. So that's just randomizing the opacity. So usefully, because we've already determined this, we don't need to do any of that. It doesn't have an atmosphere. But what I will do is I'll break out gas giants separately, because the gas giant atmospheric composition is going to be different from rocky planets. Some of these can be calculated a little bit more accurately now. The job for today is to really flesh out all the data points that are required for determining whether or not a planet has life. Because up until now, planets have been quite vague in how they're generated. So you'll get things like an Earth-like up against an M-class star because it can have liquid water at that equilibrium temperature. Taking like nothing else into account, if it can have liquid water, it must be an Earth-like. We're now doing it properly, so it has to tick many more boxes than just having liquid water. Things like there was a data point I was reading about oxygen saturation and how it's not the amount of oxygen that's in the atmosphere that's important. It's the partial pressure. Someone who does diving probably knows a lot more about this. If air pressure increases with the same amount of oxygen, it becomes toxic. So as air pressure increases, you need less oxygen, and obviously there's an upper and a lower bound on that. But it's that oxygen partial pressure which is the important thing for being breathable and not being toxic or not enough oxygen. Yeah, and of course it has to smell nice too, obviously. Right, let's see what that's actually spitting out now. You know what? I'm going to stop that because that was going to do something crazy, because I removed the bit of code that was deducting the mass from the protoplanetary disk. That would have been bad. We would have just had an infinite loop crash. Ignore any scraping noises you might hear. Claire's just put a fish tank on my desk. I'm not quite sure why there's a fish tank on my desk. Is this for a baby bird? Ah. So, anyone who's been watching the stream regularly will know that we nursed a baby sparrow back to life a few weeks back. And that baby sparrow is now doing wonderfully, actually. He's joined the flock of other sparrows that live in this area and seems to be getting on with its life quite happily. However, we have a nest of pigeons in our tree, and the mother pigeon has done a runner, has just left them, abandoned them in the nest, and we've been watching it to see whether or not she comes back, and she hasn't, so it looks like we're looking after 2 more baby birds. For some reason we've all of a sudden turned into like a bird rehabilitation clinic. It's an empty fish tank. We're using it as a what's the word? Incubator. I wanted to say insulator. No, it's an incubator. We've got a little heat mat and everything to keep the birds warm. I also have a giant fish tank next to me. We've got a 6-foot tank. I'm not sure what the literage is. It's huge, and it has a single goldfish in it, which we got from a fair about 10 years ago. And that single goldfish is now like a foot long and still doing quite well. Mr. Bryan, yes, I also watched the Grand Prix. It was a good one. I was biting my nails most of the way through the last few laps with Verstappen chasing Lewis Hamilton down. And then typically Verstappen caused an accident. Yeah, I've never seen Max Verstappen behave like, I don't know, like a petulant child as much as he did in that race. Mind you, Lando was being a bit petulant as well. Okay, Galaxy, what have you got for us? Okay. Yeah, see these values, I'm going to have to go through and double check them, because if it's 0.8 of Earth's mass, then surely the gravity should be lower. I mean, granted, gravity is based on density as well, but yes. Giga years, yeah, so it's billion years. Hang on though, that density value looks weird. Yes, the solar system is fixed. Yeah, there must be a display error because well, I say that. No, it must be because unless that's what's driving the gravity up artificially. Is it going to be Earth or is it going to be Saturn? Hurrah, it's Saturn. Yeah, so the long range sensors won't have anywhere near as much of that amount of detail on them. So generally speaking, it will show you things like the orbital data for that body, because it's the sort of thing that you can see from a long way away. I mean, we can work that out from Earth with telescopes. So yeah, whether or not it has an atmosphere, we can determine that with a telescope. So anything you can determine with a telescope from a long way away will be on the long range sensors. Things like the core and mantle and all that sort of thing, that's going to be on the short range scan. And things like atmospheric composition, surface composition, whether or not there's life, all of that's going to be visual range. The short-range sensors will tell you everything you need to know from orbit. As long as you're within visual range of the planet, you can scan all those sorts of things. Again, you don't really need a probe to see the chemical composition of an atmosphere. You need only to have the sun shine through it, and you can separate out the spectrum. The probes are for retrieving samples, not necessarily for performing scans. So the ship's sensor array will be perfectly capable of performing all the scans you need to perform. When you send a probe down, you're there to grab something physical. Yes, Ian, it is actually. I think I've added it rather than taking it away. The conversion's really simple, so I must have sleepy brained that one. Okay, so we got a few discrepancies to sort out there. I always fail the feature creep test, don't worry. Yeah, I'll have a look at how the density is being calculated in a sec, because that's clearly wrong. Where's the box? There's the box. The ship will have practically an infinite number of probes. You just need to make more. So there'll be a 3D print lab. Yeah, so that should be subtracting 273, not subtracting minus 273, which of course is adding it on. So yeah, that should be right now. Right, so yeah, so the density value, we're literally just making it float and printing it out, so there's no calculation going on there, which means it's broken in here. Checking my math a minute. Right, so volume is 4 divided by 3 times pi times radius cubed. So that's right. And then we've got density from mass and volume. So density is mass divided by volume. Yeah, I wonder if it's the unit of measurement that's the issue here. Funny enough, I made myself a handy table of densities just to get myself on track. Right, let's see where we're setting this. So we're setting it here. This is the old code that's no longer used. And we're setting it here. It's the only places it's being set. Let's just see whether we're setting this anywhere weird. So that's the old one, which we no longer use. And that is the new one. Yeah, so first it calculates the volume, and then it calculates the mean density. Let's give that a whirl. That should be it, shouldn't it? Oh yes, thank you, sorry. I'm thinking in 2 dimensions again. You are quite right. Well, hopefully this will sort out the gravity calculation as well. Although, yeah, because if that's in kilometers, yeah. I'll have a look at them afterwards. This is one of the joys of doing the live streams. You guys point out things that I do wrong. It's very helpful. Right, let's go over the terrestrial planet. Well, that's a more sensible value, isn't it? Yeah, so the stupid density was obviously affecting the gravity calculation as well. That's a lot more like what you'd expect. More mass than Earth, a greater average density, because I think Earth's average density is like 5,500 kilograms. Thus we have more gravity as well, so that's good. And the Celsius is correct as well. Yeah, Alan, it's a fraction. So that would be 121%, not 1.21%. Yeah, so this is the mean density. And obviously we then calculate the actual layer densities, which we're not doing right now, so that needs to be added back in. Core rotation, that's something that needs adding, because obviously the core rotation determines the magnetic field, and then that determines whether or not that planet's holding onto an atmosphere. Obviously gas giants don't matter quite so much because they're massive enough that they hold on to the atmosphere anyway. Okay, so the radius is looking better now. I think the biggest issue here is that these gas giants are generating with nowhere near enough mass. So for it to be a gas giant, it must be, in the region of 10 Earth masses, which it isn't. So yeah, I think we fixed that. Yeah, I think the gas giant radius was being thrown off by the density value being wrong. Unless there's a specific one that's broken. No, these seem okay. Yeah, these long values, they're only displayed in literal kilograms. For debugging purposes right now. Once I'm happy with the values and I'm satisfied that it's all being calculated correctly, then I can start condensing those into more human readable numbers. This is weird. So according to this, it's got half of Earth's mass, and yet the gravity is 928 times Earth gravity, which is very, very wrong. Let's check the other one. Oh yeah, we're not calculating these yet, don't worry about those. Oh, I think I know what it is actually. I reckon that the display is probably displaying the wrong version. It's probably displaying the initial mass, not the final mass, which means it's not showing the true mass of the planet. Let's just get back to here. So that would be, yeah, that's the problem. That's the wrong mass. We want the final mass. That was just a display bug. Exactly that, yeah. So it was showing you the mass of the rocky core, not the gas envelope on top of it, which is why it's just a tiny value. It doesn't quite explain the extreme gravity though. I mean, that should be gravity at sea level or 1 atmosphere of pressure, which on gas giants is actually really low. Now, I think Jupiter gravity at 1 bar. Yeah, so Jupiter has 2.5 times Earth gravity at 1 bar of atmospheric pressure. So that's kind of our baseline. It's definitely adding the mass. Yeah, do a bit of a tab purge a minute. Right, so we do our initial rocky core, which is our initial mass. Then we decide whether or not it's a gas giant, and that's simply based on those curves. Yeah, so we're not adding atmospheric mass to that. Right, and then we do the gas envelope. So we're taking the mass from the float curve, so that is everything from 130 Earth masses all the way up to 4,000 Earth masses of gas envelope. So that's the equivalent of 13 Jupiters, which is kind of the border where Jupiter would be a brown dwarf. And that is kind of the borderline where you get from super Earths transitioning into mini Neptunes. And this is based on distance from the star. So the colder it gets, saying that, yeah, so the colder it gets, the more volatiles there are in the protoplanetary disk. So that's right. That's good. Yeah, so we're adding the gas envelope mass to the core mass, and then we're timesing that by 10 to the power 24, and that's our final planet mass, including the gas envelope in kilograms, which of course we're then deducting from the system mass. And then the very next step after that, we are working out the radius. Again, we have our mass. And we're dividing that by Earth masses because this is the way that the table's been organized. Ooh, actually, yeah. So we've skipped the gas giant. That's why. So of course it's calculating all this without a radius value. So it just so happens that handy dandy table actually had a gas giant range on it, I believe. Yeah, hydrogen to helium. Hang on, bear with me. Annoyingly, this data I have only goes up to 32 Earth masses. I might have to extrapolate that out a bit further. But just see if I can do this with a lookup table real quick. Bear with me 2 secs, guys. Sorry about that, I was just helping Claire out. I'm going to have to shoot off in about half an hour. She needs my assistance with these 2 birds. They're very cold and they have fly strike as well, which doesn't help. So we need to get them cleaned up and fed and everything. So I had a really nice graph that showed the maximum radii of Jupiter-likes. Here we go. So yeah, so maximum radius really is only about 2 times the radius of Jupiter. So kind of what we want to do really is we want to map that to a range. So if we do a map range and this is a temporary solution. I should be allowing to use that actually. Can we use giant numbers? Yeah, we can. Great. It makes life easier. Right, so that being the case, we take Earth's mass times that by 10. So that's our minimum value. It's going to be slightly weird because that's it's going to have floating point errors despite being a double. And then we want our final planet mass. So maximum radius is going to be approximately Earth times 2. And then the minimum radius suppose we're looking at mini Neptunes. 1.6 times Earth. Oh, hang on. No, that's Jupiter, isn't it? Not Earth. So that's 69,911 times 2. That's our maximum radius. And then 6. That's our minimum radius. And then we just need to put in the giant number, which is 13 Jupiters worth of mass, which is all them zeros. No, it's not. It's not enough zeros. That many zeros. Crazy Ghost Hunters, yes. Yeah, anything that has a physical effect associated with it in the game, we will try and model accurately as much as we can. Right, so this is a bit of a band-aid approach. I'm going to get the actual lookup table for exoplanet data, and we'll extrapolate this more precisely. But for now, just to verify the numbers, it should suffice. Okay, that's looking more like it. The density is way too low. Now, stars are generated based on their class. So for main sequence stars, there's a fairly linear relationship between mass, luminosity, and temperature. That's a good question. It's set like that because I was testing something once and it's kind of stuck. Right, so to aid in understanding what's going on with that data, I think what I'll do is we will pull out object type. Do this with the select actually. Yeah, I'm about to make that make more sense. So we're dividing it by Earth's gravity, and what we actually want to do is we want to use Jupiter's gravity. And also Jupiter's mass and radius for gas giants. So we got a sensible point of comparison. Okay, so we'll pop that in there. Yeah, we'll do the same for this one as well. So collapse that to gravity, isn't it? Okay, so that's the gravity, that's the mass. And of course, this is not a percent, it's a multiplier. Of course, a complication of doing it like this, and again, this is just for testing purposes, it's not going to stay horrendous like this is we need to switch that depending on whether it's a gas giant. Yeah, so really we need to capture the gravity in addition to the type. And then we need to output a string. There we go, text. Actually, so I'm going to do 2 selects on this. Just to be awkward. So no, don't care about stars, do we? So we want gas giants. And then everything else. Hi Sarah, yes, very well, thank you. And then we just take this. So when it comes to making the actual final readout on the display, I will have to do something similar to this, so that we can define whether or not we are comparing to Jupiter or Earth. Obviously, we want to compare gas giants to Jupiter because it makes more sense that way. So this one is going to be Earth, so it means we need Earth's mass in those boxes. No, we don't want Earth's gravity. Which is 0.807. So we need that. All of these. These ones, we just need to fill in the gas giants with Jupiter's gravity. And that should give us our ugly but functional output. We just need to put in do. There used to be a thing with format text where you could move the fields around up and down, and I don't know how you enable these anymore. It doesn't seem to matter what they do. Like you just literally put a blank node in there, nothing in it, and then just do something there. It's still all grayed out, and I don't know how to ungray it out. So if anyone does know how to do that, please let me know. Yeah, absolutely, Team Ruddy, well done. Yeah, this is very much a collaborative effort. I think that's the fun of doing these live streams, is that everyone gets to be involved. Sometimes creatively as well. Ray marching is used for the atmospheres. The surfaces are just procedural textures, essentially overlaid noise layers. Yeah, all backers are named in the credits. And right now, in terms of the code, it's just me, although we are actively recruiting for more people. We've got several hundred job emails for the concept artist role, and we're expecting a similar amount for the various coding and graphic design roles as well. So there will be a team. It's just it's a slow process building up a strong functional team. Just test that actually worked. Yeah, we don't want to just take on the first person that applies. We want to make sure that we build a strong team of like-minded individuals as well. Yeah, not necessarily until the end of the year. We're hoping to have, we've got 2 concept artists engaged right now, doing some concept work for us. They're just a one-off contract, but assuming that goes well, we will be contracting them for a lot more work. Concept art really is like the first piece of the puzzle. Apologies for any noises in the background. That is Claire doing her animal husbandry work. That's good. That's interesting. Why was it using the Earth? Ice giant, gas giants. Just get an idea of what the actual type is coming out once, because I'm not convinced that that's repulsing the correct value there, and I think what's happening is it's not picking up the correct planet type, and that's probably because when we're doing our final planet type here, obviously these two are being ignored. It's only going to be working on these two. It must not be hitting the right boxes. See, that should capture it, but let's see what it says. I've never really used other game engines. I've only ever really used Unreal. I looked at Lumberyard briefly, but yeah, I would say right now, I would say Unreal is ahead of the game in terms of its feature set. Okay, so that one's a water world, which is why it's picked up Earth. That makes sense. So yeah, that's just got itself confused, really. Also, a water world. Interesting. That's more like it. wrong way around. I'll explain the weird number. The ship interior is static, and we move space around the ship. Greetings. Today we're working on the planetary data and refining the structure of the worlds ahead of putting life on them. Various calculations like atmospheric pressure require things like accurate gravity, which hasn't been the case. We've had some weird readings coming out, so I've just been going through and sanity checking that. Deleted an extra 0 there. So just comparing mass to Earth. And we need to do the same with Jupiter. Here's what I prepared earlier. Give us our mass value as well. World, don't want that one. Okay, so this one's saying if it's 1.5 times Jupiter's mass, it's 12 times Jupiter's gravity. I'm going to have to spreadsheet that to make sure that that is in fact the case. Doesn't seem right. It's also generating a lot of water worlds. So we'll refine that with the gas envelopes just to see whether it's truly a water world. This is a very dense world, hence the slightly raised gravity value. A small planet. Dissimilar from the moon. So the data looks good for terrestrial worlds, but gas giants definitely need some work on there. Yeah, the mass value changing when I put it in the box is because of floating point errors. Like, this is a 64-bit double, but it's still a floating point, so you get those floating point errors. They're unavoidable when you're dealing with numbers that big. We can avoid using raw kilograms and just use like 10 to the power 24 instead, and that stops the rounding problems. The doubles not floats? Sure. It says double float. Thanks, Zelaf. I'll have a look at that. But sadly, I'm going to have to shoot off. So I'm sorry this was only a 2-hour stream tonight. Claire requires my assistance, but when I'm done helping Claire, I shall get back to this, and I'm going to do some spreadsheets on those calculations just to make sure that they add up, and then I'll put a build out later on this evening. The Earth planets, so the Sol planets, are no longer all Earth, so that's fixed. The black holes are all fixed. And they also have planets now, quite far out and obviously very dark, but planets are actually there. And there's a few other fixes as well, so I'll put that in a build later. But yeah, so sorry again for the short stream, but I shall see you all on Wednesday, where we shall pick this up and carry on. And hopefully by Wednesday I'll have a lot more of the background work done, so we can crack on with those life calculations, which I'm super excited about doing. Thank you. Yes. All right, thank you guys. I shall catch you on Wednesday's stream. Bye for now.